gentlemen. My name is David Davis. I'm the chairman of the Society for Nautical Research, and we're delighted to be the host organisation for this evening. I was particularly delighted to be able to invite Dr. Margaret Scotty to give this EGR Taylor lecture tonight. Margaret is the author of this book, Sailing School, Navigating Science and Skill, 1550 to 1800. When I read it last year when it first came out, I was struck straight away by the fact that this is one of those books that completely changes one's understanding of a particular topic. And in the case of Sailing School, Margaret takes the question of how navigators actually learned to navigate over a period of 2.5 centuries. And she does so in an incredibly original and refreshing way, looking at particular centers at particular moments in their history and at the developments that were going on there. And she takes that into an incredibly broad discussion of the subject and comes to some very, very thought-provoking conclusions. The breadth of research in this book is remarkable. And it's, I think, very, very fitting that she should be giving a lecture in memory of EGR Taylor, whose theme, whose life's work this very much was. Margaret is Associate Professor at York University, Toronto. She is currently working on a number of themes, including the use of logbooks in the same time period, in the use of textbooks, how they were actually used in the practical teaching and application of navigation. And I really look forward to the publication of her next book and to seeing further work from her in the future. But in the meantime, I'm absolutely delighted to be able to introduce Margaret to speak to us this evening. Thank you.
Good afternoon. First of all, I would like to express my thanks to the Royal Geographical Society for hosting this event, the Society for Nautical Research for the invitation, and Dr. Davies for his kind introduction. It is a great honor to be included among the group of speakers who have helped to continue the public recognition of Professor EGR Taylor's legacy. Although I'm only the 8th woman to give this lecture, there are now more women involved in maritime and mathematical history than ever before, a development that surely would have pleased Professor Taylor. Now, my story today starts in Amsterdam, just outside Centraal Station. Although I am an early modernist, this is a recent story. In the summer of 2009, when I was taking a Dutch language course, I had coffee there with an eminent maritime historian. Halfway through our meeting, he was explaining some technicality about computing a vessel's position. Well, he said, the Dutch used tables, but the French used instruments. Oh, I said, that's very interesting. Why? Oh, he replied, it doesn't make a difference. They both get the same answer. Now, to me, as a historian of science and a historian of information and the book, this is a very intriguing puzzle. I'm interested in how people have used different instruments at different times and why there are variations. It certainly seems noteworthy that some practitioners at sea used this, while others used this. The solution on the slide at this moment requires considerable comfort with dense columns of numbers, while the second option requires a steady hand, but little else. In any event, propelled by that casual statement about national differences, not to mention several cups of strong Dutch coffee, I headed to the archives in half a dozen countries to understand why exactly navigators approach standard tasks in different ways. Was it a question of national pride because certain instruments were developed by compatriots? Were specific instruments mandated by the state? Did it have to do with influential teachers or instrument makers or other factors? Only a short decade after I had that meeting in Amsterdam, I succeeded in laying out some answers in my new book. Sailing School, Navigating Science and Skill, 1550 to 1800, is a comparative history of navigational training in Spain, France, the Netherlands, and England. In my book, I have worked to recover details about the scientific and technical expertise in various maritime communities, including not just navigators, but all of the mathematical practitioners who taught them, built their instruments, and drew maps for them, even taking into account that many ships were multicultural and polyglot. There were, nevertheless, interesting differences along national lines. In many ways, my work takes Professor Taylor's haven-finding art as a starting point, and then builds on her capsule biographies of Tudor, Stuart, and Hanoverian practitioners. I have chosen to extend her approach to other countries and to connect with the histories of science and the book in order to be able to answer new questions. In our time today, I will begin with a few thoughts on the advantages of comparative history, supported by some familiar early modern voices. To explain the larger system, I will also briefly lay out the shared elements of the program for training navigators. I will then offer two case studies that allow us to zoom in on national differences. The first will focus on how mariners estimated the speed of their vessels, and the second on how they determined their position. Now, maritime history has rarely been comparative, but it is extremely valuable to reframe it this way. First, I would like to suggest we need to look for common ground, which in turn will allow us to better understand differences. Maritime and naval histories tend to stick to national boundaries. Professor Taylor, in her 1956 Haven Finding Art, actually did consider seagoing peoples from around the world, ranging from the Phoenicians to Arab navigators to the Portuguese and English. But many others have not done this. The majority of 20th century naval and maritime histories were written along patriotic lines. British authors tended to have a particular interest in what made the Royal Navy so dominant. The Dutch asked, why did they fall so far from their impressive heights after the 17th century? As for the French, they wondered why their navy never amounted to much. Was it true that Louis XIV favored his army? Of course, there are many factors behind these authors' decisions to focus on national narratives, ranging from who had access to which archives, directives from publishers about what might sell, and last but not least, the historian's linguistic limitations. However, if you listen to contemporary actors from the early modern period, many were remarkably international in their outlook, looking assiduously beyond their borders. For instance, Samuel Pepys, the famous English diarist and naval administrator, was very concerned about his nation's rivals. When he was just a 31-year-old clerk of the Acts in the British Admiralty, he was asked to write a history of the Royal Navy. He undertook his research very systematically in the 1680s and returned to it the following decade. The manuscript that survives with his point-form notes gives us a glimpse into Pepys's worried mind. He was sure that England lagged behind her neighbors in almost every possible way: legislation, publication, all things navigation. Pepys queried, "Our first navigation book, the Rudder, a translation from French. Are other first books all translations?" The Duke of York agrees with me in the excellency of the naval instructions of France as they are printed in the Book of Ordnance, France having improved on ours and the Dutch. The backwardness of England in comparison of France in all things relating to the science and practice of navigation. Pepys was far from the only administrator or leader to be focused on what was going on beyond his borders. In his capacity as Ministre de la Marine, Jean-Baptiste Colbert was similarly interested in what the neighbors were doing. But if Pepys thought the French knew the most, from the French perspective, it was the Dutch. Meanwhile, the Dutch, said one of Colbert's correspondents, they have schools for pilots. It's for that reason that those pilots that we have of theirs are incomparably better than those of all other countries. Clearly, Both Pepys and Colbert were extremely interested in how other nations trained their navigators. Every nation in maritime Europe was concerned with keeping their shores safe and their reputations forbidding. But it turns out that all of these polities were quite aware that they were dealing with the same problem: how to make navigators in a hurry. And each worried that certain neighbors were managing to do this better than they were. Pretty much everyone looked abroad for insights. This was an age when, rather than trying to keep secrets, Europeans were copying each other. The historian of Iberian science, Maria Portuondo, has called navigation and cosmography the secret science. But she was referring to the early 16th century when Spain was trying its hardest to limit access to manuscript charts about newly discovered regions of the world. By the late 16th century, by contrast, virtually nothing remained secret. Why? Because the advent of print changed everything. Once charts and textbooks were published in Amsterdam and elsewhere, the proverbial horse was out of the barn. By the 1580s, Northwestern Europeans were able to access key texts written by Iberian navigators, and within half a century, they were completely familiar with the main underpinnings of the new science of celestial navigation. They respected and admired the success the Spanish were enjoying, and therefore copied them as closely as possible. Once again, we know this thanks to the meticulous records of men like Pepys and Colbert. Colbert, whom Jake Saul has dubbed the information master, collected great quantities of data from maritime men around the country. Here we see a memoir describing what was covered in navigation courses, how the teachers ran their classrooms, how many students they had, and which of these passed their exams. There are several dozens of these reports from the 1680s, which was just when Colbert was in the process of setting up schools and rolling out a national naval code. Admittedly, some of these reports might be overly positive, although wouldn't you be too if you were reporting to Colbert? They do offer valuable first-person evidence of how sailors were being taught. When it came to naval reforms, Pepys had rather less authority than Colbert. Our chair this evening, Dr. Davies, would remind us that the Royal Navy owed its development in the 1680s to Charles II instead. However, Pepys still made some important bureaucratic changes in the Royal Navy. In his research notes for the history of the English Navy, Pepys drew up lists of Spanish books he wished to acquire from abroad, and others that he wanted to translate into English. I don't have an image of that volume, but here is his systematic catalog of everything published in English about navigation. As I noted earlier, Pepys trawled through sources for ideas on how to set up training schools for junior mariners. It is here, in the midst of Pepys's very nationalist project, that we find yet more outward-looking comments about how to teach navigation. He noted, "We have borrowed also from the French, and they, I think, from the Spaniards, the king's late institution of the mathematical school." The Spanish, as Pepys noted, had a school, a Seminario de los Niños, founded in 1552 at the Casa de la Contratación. By the time Pepys made most of his notes in the 1680s, there was also this second school, the Seminario de San Telmo. These pioneering state institutions had standard features. The professors in these schools relied on lectures, textbooks, and examinations, a throwback to the university education that the instructors themselves had received. This formal approach to education was completely illogical for the barely literate pilotos in the early 16th century. But no matter, it was this system that Colbert and Pepys and their monarchs wished to emulate, and they did so. The French founding schools in Dieppe and Havre de Grace in 1665, followed by 9 more institutions by 1681, and in London, Charles II founded the Royal Mathematical School in 1673. Elsewhere, there were smaller independent schools run by entrepreneurs who often wanted to sell instruments, books, and lessons to each of their students. In this period, at the end of the 17th century, we find similarities and cross-pollination across countless borders. Dutch mariners traveled to teach navigation in Denmark and Russia. German and Scandinavian sailors took classes in Amsterdam, and so on. I want to take a moment to emphasize the similarities within printed manuals as the Iberian textbooks moved north. One thing that I have done in the course of writing my book was read several hundred navigation textbooks so that you don't have to do so. Some are charming. We find glimpses of authors' personalities and publishers' promotional spirit, but they are admittedly filled with page after page of definition and practice question. Remarkably, we often find the same diagrams in English, Dutch, French, and Spanish textbooks and manuscripts. Here are some spinning volvels to help determine the time of the tides. And here are diagrams to illustrate the sun's declination, a step towards finding one's latitude. This brief overview was intended to demonstrate that European maritime communities deployed remarkably similar strategies to solve a common problem: how to create skilled navigators efficiently, especially navigators who could work through the complex new formulas required by celestial navigation. Now that we have established how much the majority of European textbooks owed to their shared Iberian origin, when we do notice differences, they become all the more significant. At this point, we can ask in more detail why these changes happened. So let us now move on to the first of my two examples to see how approaches to nautical education and practice varied subtly but significantly across national borders. Imagine yourself on the pitching deck of an early modern ship with gray storm clouds obscuring the sun and nothing in sight except for white flecked waves. Your challenge as the navigator is to determine the ship's current speed. This essential task will allow you to find your vessel's position relative to its previously known location. After multiplying your best estimate of the speed by the distance traveled in a particular direction, you would then compare that dead reckoning to celestial altitude observations to confirm your latitude. However, with no visible landmarks at the combined mercy of tides, currents, waves, and wind, how could an early modern sailor even begin to assess how fast his ship was sailing? This was widely considered the navigator's most challenging task. In 1643, the French Jesuit Georges Fournier claimed, "A smart man knows the difficulty, indeed the impossibility, of making a fair estimate." 20 years later, the leading French navigation teacher Guillaume Denis declared that the route is the most difficult thing to estimate because there is nothing but prudence and experience that can produce it, and even after all the precautions one can bring to it, one is often wrong. While the Dutch were more optimistic than the French about the abilities of their navigators, the Dutch term for estimating is gissen, the root of the English verb to guess. Prominent authors repeatedly intoned a common motto, gissen valt missing, which translates roughly to guessing leads to missing your mark, or guessing is messy. Through the ages, prominent figures have attempted to solve this problem mechanically. The ancient Greek Vitruvius devised a geared water wheel that recorded a ship's progress by dropping small pebbles into a basin. In his weighty 1643 nautical tome, Georges Fournier illustrated a machine that had been developed on the Mediterranean. Even Leonardo da Vinci gave some thought to a solution, although sadly never illustrated it. So everyone agreed estimating speed was difficult. But when we dig a little deeper, we find that this crucial daily task is handled in markedly different ways. And this is where things start to get interesting. If you were an English navigator, you would likely throw the log and line off the vessel's stern. This simple wooden chip or log was attached to a line. You would throw the log off the vessel's stern and time how quickly the rope slipped out. This invention was first mentioned in the 1570s. By the 1620s, the English mathematician Edmund Gunter introduced the concept of tying knots at regular intervals to simplify the calculation of the rope's length. For every section of the rope that slipped overboard, approximately 40 feet at a time, the boat was traveling at 1 knot, which came to represent 1 nautical mile per hour. The French loved this tool as well. Here is the first known illustration of it in Champlain's 1632 Traité de la Marine. A Dutch navigator, however, would take a radically different approach. He, in fact, needed nothing more than the water itself. Once he sighted a substantial fleck of foam from a white-capped wave near the bow, he would begin counting 1 and 20, 2 and 20, 3 and 20, until that same fleck had traveled some 40 or 60 feet past a second mark on the hull. If the first method depended entirely on instruments for timekeeping and for distance, the second, less mechanical method, it was the navigator who supplied the clock and the ocean that supplied the distance marker. When we find mentions of the Dutchman's log, that actually refers to the fleck of foam. The question is, how did Dutch navigators learn to keep time so accurately? In Dutch, and only Dutch textbooks, we find that authors spend pages at a time encouraging their sailors to look at the water, to memorize its appearance when their boat is traveling at a known speed, and to perfect their internal mental metronome so that they can always count at the exact same pace. Klaas Vogt, writing in 1695, invoked the language of the medieval memory arts. To gauge the appearance of something intangible, one must daily observe the speed of the ship through the water and impress that in one's thoughts and remember how many miles the ship travels in one day. And that way, in time, one learns to make good estimates. As Taylor reminds us, traditional coastal navigators derived much of their professional reputation from their ability to memorize the geographic features and hazards of their sailing routes. The same capacity continued to be essential in the age of transoceanic navigating. A good memory was inescapably twinned with diligent observation. But Dutch experts also wanted to teach more standardized approaches. In 1662, Joost van Breen devoted an extensive chapter to the observation of distance, explaining exactly how to calibrate one's internal metronome using a sand glass. With the help of this little glass, you get used to a certain steady counting, so that every time the glass runs, you count the same number. For this, one must at first frequently do and redo it to get firmly used to it. And having gotten very accustomed to it, it will remain useful all your life. Such metrical counting blurred the line between skilled human and instrument. Whereas sand glasses were notoriously inconsistent, humans could train themselves not to lose time. Joost van Breen was very specific about how to act as one's own timekeeper, from where to stand on the deck, far enough back to avoid spray coming over the bow, but somewhere where you could still see the forward mark. And at night, you should have the distance since it was harder to see the water. He also gave concrete numbers. When observing a fleck of foam shooting past the hull, if the navigator counted up to 409, the ship was sailing at 1 mile an hour. Whereas if you reached only 102, that indicated a faster 4 mile an hour clip. Van Breen warned that it can also happen that your standard count could become too slow or fast, but if that happens, you should just go back to practicing with the sand glass and you will learn to stay regular. He also provided a helpful formula should the first hourglass break and its replacement run faster or slower. This was not haphazard intuitive counting. The navigator even needed to modify his mental gauge of progress if he switched to a different type of ship. It was essential to be mindful of the vessel's general construction, the amount of sail she was carrying, how recently she had been careened, and even her national origin, which affected the shape of the hull and her position in the water. Contemporary French and English manuals contain no comparable strategies for honing one's senses or developing this expertise. One of the earliest English descriptions of the log and line mentioned that some sailors used to recite certain phrases, some number of words or such other like, to help them time the log's motion, but no record of any such phrases survives. The French, for their part, seemed particularly daunted by the impossibility of devising rules about how to judge speed. As we saw, according to experts like Fournier and Denis, the vessel's progress was subject to all the vagaries of the sea and thus would lead even the most experienced navigators to make frequent large mistakes. Fortunately for aspiring navigators, their other daily tasks were not considered this difficult. My second example, with which I began this talk, has to do with determining the vessel's position. Although this was easier than estimating speed, it still had its challenges. Now it is time to see if we can get to the bottom of why Dutch navigators used tables, but French navigators used quadrants. Both are helpful tools for determining location, but as I mentioned, they require different skills and can suggest that each workforce had different competencies. We can once again find evidence of how various crew tackled this problem through careful analysis of textbooks. Early modern navigators thought of their progress in terms of a series of sailing triangles. This meant that their current position could be found through a number of different methods, including geometry, trigonometry, and soon, instruments. Here we can see calculations done geometrically. The 17th century saw the development of two important new mathematical tools, logarithms and trigonometry tables. The printing press made it possible to more easily reproduce these dense tables and with fewer errors. As a result, trigonometry became the fastest way for navigators to make their daily computations. Virtually all Dutch and some English handbooks were issued with extensive tables at the back, but these were found much less frequently in French manuals. Once the navigator had obtained one of these elusive estimates for his vessel's speed, he needed to multiply it by the length of time he had sailed on a particular course, the heading or direction. He could consult run tables, but if the course was more complicated, he would need to work out the series of triangles trigonometrically. Here we can see a Dutch student needed 5 pages of calculations to obtain a single answer. With all this work, the navigator could come up with a very accurate position. Certain instructors, particularly in France, questioned whether all this time-consuming work was worth it. Guillaume Denis worried about the difficulty the Dutch encounter with their numerous calculations. He deemed these to be a serious discomfort. Instructors started recommending that navigators could take a shortcut, calculating the total displacement here on the right, rather than add up each leg of the journey on the left. They admitted that this could introduce some degree of inaccuracy, but often time was of the essence. All of these calculations were daunting. It did not take long for innovative mathematical practitioners to devise instrumental methods. According to the marketing pitches from their inventor, these new tools would allow men to avoid computations altogether. We once again find national preferences for instruments. The English preferred to use Gunter's scales, designed by the English clergyman Edmund Gunter in the 1620s. The French called this the échelle anglaise. They were marked with trigonometric, logarithmic, and surveying lines. For their part, the French turned to graphical solutions, various types of quadrants, which, like the Gunter scales, were marked with trigonometric lines. Here is the most popular type, the cynical quadrant, or in French, the quartier de réduction. This one in particular, you can see, was used quite frequently. To find one's position using these, you simply needed to observe your direction with your magnetic compass, and then, using the distance you had computed with the log and line, use the thread in the bottom left corner to pinpoint the position on the surface of your course. The thread becomes the hypotenuse of your course. These were often engraved paper broadsides, glued onto wooden boards or cardboard. And some of these quadrants had different markings on the back, enabling them to be used to take vertical measurements for determining altitude and, less frequently, other astronomical questions. Thus, these graduated quartiers de réduction could help navigators determine their current position without any mathematical calculations at all. Here is an example from across the channel where you can see William Spink in his student notebook learning to use both the Gunter scale on the left-hand page and trigonometry illustrated here on the right. According to Elizabeth Hébert's excellent analysis of a 1760 French manuscript workbook by Jean-Baptiste de Nonville, the English just simply did not use cynical quadrants. The French, for their part, relied on them for more than a century. There are additional differences in national practice, which I have found in my research. When it came to the vessel's position, if we needed to reconcile any difference between dead reckoning and the daily observations, the French were very fond of a set of rules called the corrections. These were invented by a Dutchman, but almost never used by Dutch navigators. The Dutch, for their part, placed great stock in tracking magnetic variation as a potential solution for determining longitude. But other countries gave up on that elusive method after a short number of years. Due to these different priorities, we then find variations in the professional examinations for masters and lieutenants in each nation. But that is the subject of another talk. So, what are we to make of all this? How are we to explain these differences? I would like to suggest that these divergent approaches to maritime technology and expertise had to do with the supply of navigators in each nation and their training. But at the same time, there were broader socioeconomic and even political reasons. In the Netherlands, substantial overseas trade produced a large number of men competing for the well-paying positions of navigator and captain. Unlike the French and English navies, where administrators such as Pepys and Colbert were habitually concerned about the caliber and education of their mariners, the major Dutch shipping companies did not even run their own schools. The free market seems to have ensured that their job applicants gained sufficient experience prior to vying for their posts. Dutch navigators felt it was worth their while to pay for private instruction in their off months, because that would allow them to pass exams and get higher paying jobs. Young green French pupils, in the records I have found, had to be bribed to stay in class. Given the greater level of professionalization and an accompanying higher degree of social respect in the Low Countries, it is not surprising that the authors of Dutch manuals were much more accepting of personal skill rather than automatically advocating their trainees turn to instruments. Acquiring these skills was certainly time-consuming, but as Joost van Breen reminds us, once learned well, they could last a lifetime. Since inaccurate, dangerous estimates could arise from imprecise equipment as well as careless, poorly trained individuals, the Dutch seem to prefer taking time to educate their navigators in essential skills. The English and the French, on the other hand, promoted instrumental solutions as a more efficient way of producing baseline acceptable results. The fact that instruments were a fallback crutch for people who were not yet skilled themselves reminds us that we should not view the history of navigation as a straight line progressing from traditional practice towards more sophisticated technology. It turns out that an expert's own perception remained pivotal throughout the centuries. But for those who lacked time to train their eyes and memories, devices and instruction manuals abounded. Given how much was at stake for the men at the helm, it is understandable that apprehensive practitioners would seek out mechanical solutions. What are the larger reasons for these differences? In this Northwestern European example, we can identify a few root causes. It is well documented that a large proportion of Dutch society had basic nautical experience. We know that as much as 10% of their adult male population worked on the water. Therefore, Dutch teachers expected mariners to have ample time to learn these elusive skills if they had not already mastered them. The French, who were quite likely to be farm boys pressed into maritime service, did not have the same familiarity with the water. Just 1.7% of their population worked at sea. For them, it was easier to simply throw the log and line and flip over a sandglass. There were also more opportunities for Dutch mariners to learn mathematics in the urban Netherlands. I have observed that French and English navigation manuals often began with the basics of arithmetic, a sign that those students might not have formally encountered them previously. Dutch youth, for their part, would likely already have taken a course at a local school and had an opportunity to work through introductory textbooks such as this one. Therefore, Dutch navigation teachers could assume that their pupils were ready for trigonometry from the very first day of class. The disparities extend to whether a nation was also politically centralized or not. The French, like the Spanish, established national schools and a standardized curriculum. The Dutch, and to a large extent the English, left things much more open to independent entrepreneurs. Competition in the latter environment tended to lead to innovation. There were countless teachers and instrument makers competing for a share of the market, with the end result being that there was something for everyone. Authors of dense, comprehensive mathematical textbooks vied for readers, just as those who promised to help sailors avoid math entirely found a ready audience. Ultimately, I believe a comparative approach is critical. If we focus on a single nation or navy at a time, it is impossible to see the shared traditions that made this system work so seamlessly. Transnational projects allow us to extrapolate from discrepancies and find significant national trends. They also allow us to judiciously fill in the gaps when archival records are silent. Exciting possibilities arise from these comparative methodologies, especially when we look to other less closely studied sources and regions of the globe. Not only are there numerous yet to be analyzed documents, for instance, those created by Scandinavian and German-speaking sailors who came to the Netherlands to take lessons, but there are even more rich opportunities to analyze practices in the Indian and Pacific Oceans. Here's just one example of a Portuguese book with annotations by an Arabic mariner. Of course, this approach requires historians to continue to extend our language skills. We must work to uncover how local communities engaged with technical tools in different ways, how they adapted them, and created their own distinctive solutions. Now, there are reasons for enthusiasts of maritime and naval history to be optimistic. Here are some recent titles, all but one released this year, which indicate that maritime historians are increasingly eager to leave behind narrow linguistic boundaries in favor of ocean-centric global projects. To conclude, if it were not for the coronavirus, I would fly back to Amsterdam to have another coffee with my Dutch historian friend. I am now better equipped to provide an answer about why instrument use varied by region and the significance of that difference. But I would also underscore that these choices, instrument or observation, geometry or trigonometry, should not be viewed as part of some great narrative of forward progress, leading Europe onward towards a perfectly rational science of navigation. Rather, those choices depend on a host of other factors. I remain indebted to EGR Taylor's important early efforts to identify the broad range of 16th through 18th century Englishmen who could be considered mathematical practitioners. Following her lead, we need to remember to look for the charismatic teachers, ambitious publishers, and those who ran affordable bookshops near each port. But it is also crucial to compare these diverse practitioners with parallel figures in other regions and nations. The mathematical skills that each of these men, and perhaps a few women, would have brought to the table were shaped by their technical training, the education available to them, their degree of exposure to the merchant community and its numerical computations, their own priorities as well as those of their government. All of these would affect the way in which they perceived the sea and the speed of the waves. Thank you very much.